the expectation of C of y of t is this pi of c.
Okay, you pulled it up.
I'm saying here's an example, yeah. Yeah, no, I said I did two things at once. I'm using linearity of the expectation.
Sure.
You know, the expectation of the difference is the difference of expectation, and we just said that is equal to pi of c. Yeah. So, so if C is bounded, then, you know, that's an example of a coupling inequality. Okay, so we all know that is a condition. I mean, with, you know, if we start initial condition x, I can write this as p to the t c at x. So I'm just writing this down in this formal language, and then this difference here, we can write that as twice the max norm. You know, c, the maximum of c. And then the expectation of that indicator function is a probability. Okay, and so typically in real problems you'll ever come across, that goes to zero geometrically fast, so we get geometric ergodicity. Always, always, always. I mean, you have to work so hard to find examples where that doesn't go to zero geometrically fast. All right, and we won't get into that in this class. I give you lots of references, but so what I want to do, you know, in the remaining 20 minutes is show you how you do this. All right. Now, there's a million ways. So people come with most ingenious, crazy methods for constructing these coupling times. It's been an industry since the 80s of people coming up with coupling times for simulation because they want to write computer code for being able to get good confidence bounds in simulation, you know. And so they use it for those tricks. So I'm presenting it as an analytical tool, for example, for proving the ergodic theorem, but it's used for simulation all the time as well. Yeah, Google it. Just Google coupling and simulation. You'll get billions of hits. So here's what we're going to do. So okay, so we have an x dot irreducible Markov chain. Eventually we're going to have to assume it's aperiodic or nothing will work. We'll see that in a minute. And what I'm going to do is somehow, I'm going to somehow make these guys independent before time t, somehow, whatever the hell that means. Well, I want, yeah. Let's see, let me be careful here. So just as before, it's really useful to have it when they couple, they become deterministic, you know? So I'm not going to look at the first time that they meet. Right, I'm going to make it the first time they meet and are equal to some special state, making them deterministic. We saw before how useful it is. And how do I say this? So this is the idea of the construction, okay? I'm going to have the coupling time like that, and these guys can be independent before that time. So I spent a lot of time playing around with this, but let's draw a picture first. I just want to emphasize that there's some x bullet. This vertical axis is a state space. So just think of the state space as being the real numbers, say. And there's a state x bullet here, and I can look at the evolution of y, and it goes around and around and around, okay? And the evolution of x, it goes around and around and around. What I'm trying to emphasize is, oh no.
You crossed.
What I'm trying to emphasize is that they haven't coupled yet. Because I'm waiting for the time that they don't meet, but they meet and are equal to this. So we might have to wait a while. But anyway, somehow they've just made a lunge. And then I cross this out. All right. Whew. Okay. All right. So I've got a construction which I cooked up with these notes to make this explicit. Because it's really, if you do this all super mathematically, it's just an ugly, unintuitive thing completely. It's so much nicer to have realizations of the process. So I'm going to make a simulation model for this. Okay. Yeah.
So when they reach X bullet, so why are they now coupled?
I get to write my own code.
So like it's like just so declared that they are going to be.
Yeah, and I claim that I can. So the point I want to get into your heads is that there's so many choices on realizing a Markov chain. When you write code, there's so many things you can do, and so I could let these guys be independent forever. That'd be a perfectly legitimate realization of the two Markov chains. Or I can say when they meet, I'm just going to pick one of them and follow it forever. That's also a realization of the Markov chain. They're both valid. And one of them is really useful, in this case, for proving stuff, and one is not. Yeah. It's this flexibility you have in writing code, you know, well, just in realizing a Markov chain. So there's sort of an easy trick here. So the construction. Did I already say construction? I said construction, but now I'm going to get seriously. So assume that there's some dynamics. I'm going to change my notation a bit here. Okay, I've been saying this without proof over and over and over again. Every Markov chain can be realized in this way. The new state is a function of the old state, and noise with the noise is IID. There's an explicit construction, I guess always. All right? And I can't tell what X is yet, so I'm just going to cheat and just define a completely independent process. Same F. All right? And they're independent of each other. So this is what you'd get if you just went crazy with MATLAB and used rand for this, and rand for this, all, you know, independent, you know, completely independent. Everything. So now I'm simulating two independent processes, all right? But then you can imagine what I'm going to do. Now I can define t. And I just put a 0 there. And now I can get away with this. And so basically, that's my y, that's my x, and I'm going to define that's not my x. I'm going to define x of t, which is equal to x0 of t for t less than capital T. And then y of t after that. And x of t evolves according to the same dynamics. And so this, again, these are ID of the same distribution. Here, I'm sampling from this ID a sequence for a while, and then suddenly I switch to this one. But my switching only depends on the past of this guy, you know. So there's no way I can predict. I don't mess up the independence, right? Because I'm making my choice to switch from this, for sampling from here to here, based on the past of this. You know, so this nx of t. It's n0 of t for t less than or equal to t. Is that right? Yeah. Let's see. Because when
there is a strict less than equal to on the upper side.
Oh, I know that, but here you see, it's only when. So maybe there's a t plus 1 here, and so I think it's correct that. Oh wait, that's not true. So at time t. Yeah, this is a new noise. Yeah, I think it's correct.
That's 1 time step ahead.
Yeah, it was 1 time step ahead. Yeah, it's the t plus 1 that makes this true. So anyway, so you can theorem, that's still IID. So this is IID as well. All right. So that's it. So that's one way of coupling is to go through and I have code doing this, and basically I just watch x0, and as soon as I see these two guys meet, I stop generating this and I just follow y. All right. So what are the questions?
Okay, I have a question. So it's like I get that this is a very general idea of coupling, and that we have 2 Markov chains, but we could have n independent processes and they all meet at some time where they all meet at some special state X bullet that we care about.
Yeah.
And then from that point forward, they all, you know, it's like we're willing or we're telling it, all right, you're going to all follow the same path now.
Yeah, we're writing a simulation code, whatever, to make this happen. That's right.
Yeah, so it's like, it's kind of like we're forcing it to be true. It's not like, I mean, like if you look at two dust pollen things, like
no, yeah.
like they're not gonna, if they meet at some.
It depends on what your goals are. See, our goal here isn't to simulate a bunch of independent agents. Our goal here is to try to simulate and get performance bound, say something like that. So this is not trying to represent reality. Right? But for example, one application is just to get a bound on the way to convergence to stationarity. You know.
Oh, yeah.
Yeah. So yeah, so I mean, this is not meant to represent reality.
Okay, so what we're trying to get it to represent is like once it hits a state, maybe we care about X star. So X star is a state.
No, we don't care. Look, there's the application. All right. So there's one application. Right? That the mean of a cost function at time t minus the steady state mean is bounded by some, the max of the cost function times the probability that the coupling time is bigger than t. And so it's little, if this is finite valued, it's little t.
I mean, I get what that you're saying. You can write code, and then like when they meet at X star, then they're gonna follow the same trajectory, trajectory,
right,
from that point forward, and you define that. So,
yep.
But I mean, in reality, the two chains, once they meet, they'll most likely go.
Well, what two chains are we talking about? Because in the course, I don't think there'll be every time in the course when we have like agents with the same evolutions. See, I don't think that's in this course. You're thinking of a different topic, where we have multiple like animals modeled as in the field modeled as Markov chains, and of course that's not applicable. That's a different topic. Yeah.
Okay, so
there's a construction for analysis in constructing simulation algorithms. This is not a way to say I'm going to want to model a bunch of agents. That's not the goal at all. So this is the simplest goal, is to prove an ergodic theorem. And we're going to see prove that value iteration converges. We're going to prove, it takes like one line of analysis. And there's all sorts of things, other assumptions. There's a thing called perfect simulation. I'd like to, I'm going to run a Markov chain. I want to find a time which I can sample, and at that time, my sample has exactly the distribution I want. The way you do it is through coupling. This is a machine. It's very, very generally used, but X and Y are not meant to model two agents. That's a different topic. Okay.
Maybe not even agents that like make their own decisions.
Yeah, but two things. Nothing to do with that. That's a different topic. Yeah, it's a different topic. Okay. X and Y are not meant to represent two physical processes in the real world. They're constructed, again, so I can get estimates on things like this, estimates on performance bounds.
So you're going to use it just to get estimates on the calls?
Either these analytical expressions or constructed simulation algorithms, which is beyond the scope of the course, but by learning this material, you can read that material and come up with perfect sampling algorithms. Okay. That's another, that's millions of examples of applications of coupling, but we're not trying to model two processes, okay? Yeah. But the questions here is like, can anybody imagine why on earth this would actually be finite? So what tools have we developed in this course to try to get a handle on this monster?
Communicating classes.
Yeah. So this looks like the kind of thing we've been working on the last week. So it looks like we could leverage our Markov chain machinery to prove that this is finite, and even to get bounds on moments. So how would we do that? We have to construct a Markov chain. So it all comes down to that, how to bound T. All right. So again, we want to use our DV3 business. We want to be able to do that. So we're going to define a Markov chain. In the notes, I call it psi of t, which is equal to x of t and y of t, but damn it, it doesn't work. It's not Markov. Now, I've constructed this thing here. I want to look at the pair process. It's not Markov. Now, x0 and why they're Markov, because they're independent Markov chains. You can write down the transition matrix, no problem. But why is this not Markov?
Like X and Y are dependent.
Nah, it's not the dependent. It's something much more specific. Because you could have dependency. Yeah.
So n phi would be, so I mean after time the noise process is not.
No, that's ID. No, this thing's ID. Nothing like that. Well, take a look at this. What's the probability that x of t plus 1 equals x prime and y of t plus 1 equals y prime, given x of t equals z and y of t equals z? I'm using funny symbols for a reason. So I notice I'm using z and z here. That's really important.
It disrespects the Markov property.
No, what? What do you mean? What?
That won't, like you can't turn that into, or you can't apply the Markov property to that. That's why it's not.
No, but why not? That's what I'm trying to get at. So what is it?
I mean, if x and y are different.
Well, the thing is that I erased it. Damn it. Remember, before t, they can hit each other all they want. You see, if you're before t, they're independent, and it's like a product of probabilities. And if you're after t, then x prime and z, y prime have to be the same because they've coupled. There's not enough information, so it's just not known. Well, I'll tell you this: it's definitely not equal to the probability that x of t plus 1 equals x prime and y of t plus 1 equals y prime, given the entire history. Wait. And why not? Because if I'm given the entire history, I can tell if it's coupled or not. I can look in the past and say, hey, did you guys meet? And I can look, And so then if I see the whole history, I can say, oh, good, you coupled, then these guys had better be the same, and you've got the regular transition matrix. Or I say, oh, you haven't coupled, well, then these are independent Markov chains. So what's the solution? One solution is to take the entire history and say, that's a Markov chain. But there's only one bit of information, literally a bit. A bit means 0, 1 of information. I only need to know if they've coupled or not. And so you'll see in the notes, I defined a new thing that is Markov, which is x of t and y of t, and then that logic function. So it is t less than t. Wait, I mean, t is greater than t. Yeah, is that it? Oh, we use the same notation as the notes. Does that make sense to you? Anybody?
Would you take off points if we just put indicator of x equals y equals x dot, and that's the logic function?
Hold on, I don't understand. 1 second. Before I answer that question, I want to make sure no, I got it backward. In the notes, I did it the other way around, so I'll do that. What was your question? Was it with a joke? Let's see the jokes later.
Like if we, instead of just defining with time, I mean, like it's the same sort of information if we just put x equals y equals x dot, right?
No, not at all. Not at all, not at all, not at all. This is saying, see, I said the reason this is important is I can tell, have I coupled yet or not? And that's the only thing you need to know. So if this is 1, it says I have coupled up till time, before time t. And if it's 0, it says I have not. So this is the only information I need. One bit of information, this is Markov. And it's Markov because you can all write down the transition matrix, I mean, I won't do it. I don't have time, I don't think. Maybe, yeah, it's, basically, if if you look at a state, well, all right, if I have x, y, and 0, 0 means I haven't coupled yet. And because of the dynamics over there, the next states, they're independent, because you're adding on independent noise. If it's equal to x, y, 0, then they've, 1, then they have coupled, right? And in fact, x has to be equal to y, it makes no sense. You have to redefine the state space as well. I mean, state space, if this is 0, then these can be anything. But as soon as this is 1, then x equals y. Makes no sense. That's what it says. I mean, we've coupled. These guys are the same. All right. All right, cool. So now we can pull out our machinery and get a bound on what? We want to get a bound on the time for this to be 1. We want a bound for that, you know. So t, that t, t is actually equal to, I'm going to call it tx dot dot. It's star star in the notes. I hate that. I wish I used dot dot. Which is equal to the minimum over t greater equal to 1, such that that psi star of t equals x dot 1. It's the same thing. It's the first time for x of t to be x naught of t equals x dot. And as soon as that's true, then this last entry ends up being 1. So it's so that's it. All right. So bring out dv3. I mean v3. All right. As soon as we've written this time as a first return time to a state, all right, then we know that V3 is characterized as that, you know, having a finite mean, or, you know, being finite valued. Yeah. So what do I need now? So what do I need? What's the machinery? So I'm not going to prove everything, but you all tell me what's the machinery. So of course I'm going to assume V3 for the original chain. But what do I need, everybody? Come on, look at your notes. You need a Lyapunov function. I'll put a little bullet there, you know, because it's going to be a function on the Lord state space. We're going to need an F bullet. And what else?
A B bullet.
Yeah, B bullet and all that, and an S bullet, yeah, absolutely. And something else that's crucial, everybody. Remember, there were two things in that big theorem. There was the existence of a solution to the equation, but also the Markov chain had to have a special property. Yep. let's call that x dot dot. Yeah. And, you know, it's not that bad. But I just don't, I can tell you're all tired of part 1 of the course. So I'm going to let you read it on your own. You know, I'm not going to derive all this for you. But, you know, if you assume V3 holds for the original Markov chain, then what you find out is that you can just add them together under very general conditions, you know. So V bullet bullet of X, Y, what's a symbol? It can be, what's a binary symbol? A B? I don't know. You know, I need some strong conditions, but you know, it's just, I just want to give you, there's one approach you can do it. You know, you don't need to do it that way, but you can. But what about X dot irreducibility? So yeah, it turns out getting, yeah, so this function will work. And, oh yeah, the F is the sum as well. I think actually it's not. It's like 1 plus a half f of x plus f of y. Something like that. So you look in the notes, you'll see something. But what about irreducibility? See, that's tricky because just imagine a Markov chain on 2 states, you know? The 1 and 2. All right, and here's my Markov chain. That's a beautiful unit chain Markov chain. I start off at 1, I go to 2. Then I go to 1, then I go to 2. Then I go to 1, and then I go to 2. All right? And suppose that x is initialized here, and y is initialized there. They go, do, 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 and they dance forever. And they never meet. They're longing for each other. They're hoping there'll be some randomness in the system that'll make them mate for life. But there is no randomization, and they do this forever. They don't even know they'll never die. They'll have to just go back and forth forever. So that's bad. So this fails. So the repair is, this is what's magic, is that we know to get an ergodic theorem we have to have aperiodicity. And it turns out that it's irreducible if and only if the Markov chain is aperiodic. And you can find this in the notes. And I think that's really awesome. And then again, the proof is, it's short, but it's just, there's too many short things. Just, when you add up all those short things, it becomes long. But it's not, it really comes to the definition of aperiodicity pretty quickly. You know, the fact that aperiodicity means that the probability of being at x dot is positive forever, you know, for all sufficiently large m. So it's not, again, it's not deep. It's just, again, we have too many things to do. So that's fucking awesome. So, and we have to stop there. So, so we have this wonderful theorem, so that under V3 and aperiodicity and x dot irreducibility, we've got V3 holding for this big Markov chain. And that has big implications, okay? And I'll give you several on Tuesday, okay? But we better stop now.
So when they merge, it ends up just being one Markov chain, right? They
Yeah,
think of it as one.
that's right. That's right. So